Good afternoon, everyone. My name is Shuo, and I'm a student from Georgia Tech. Since we don't have enough time, I guess I'm going to make this as short as possible, like roughly 10 minutes. During my study at Georgia Tech, I also received very helpful support from Vivek. Before my PhD study, I attended Vivek's programming language class, and at that time, I was just starting my journey to compilers and programming languages. So this is the topic of my today's talk, which is joint work of myself and my advisor, Qirun Zhang. SMT formulas are like very popular ways to encode verification conditions and other constraints in program analysis and verification. But because of the inherent reason that many theories are undecidable, solvers are inherently incomplete, so it may fail to solve formulas. So this is like a lightweight way to retrieve some unsolvable formulas by a very simple idea, which turns out to work in some cases. As you will see, this actually leads to a kind of a special usage of parallelization. In a normal parallelization work, you might want every job to complete. But in this case, we actually only need one job to complete in order to get a useful result. This is the problem that this work is targeting. It's solver's incompleteness, and in theory, this cannot be avoided because of undecidability. In reality, a solver may report unknown even within a very short time because of some unimplemented details or some other reasons. So the idea of this trick is very simple. Instead of solving the original formula, we try some restricted versions or relaxed versions. In this case, the restricted version is like restricting A to be 1. It's obvious that if the restricted version is satisfiable, then the original version is also satisfiable. On the other side, it's a relaxed version. It is relaxed because in the original version, we not only require the thing on the left-hand side to be an integer which is equal to 1. We also want it to be a sum of 2 integers. That is kind of like another constraint. So on the relaxed version, we just relax that constraint and just use a variable to denote the subterm. So this somehow provides one-sided guarantees in terms of formula solving. If the restricted one is satisfiable, then that means the original one should also be satisfiable. The other case is if the relaxed version, even the relaxed version is unsatisfiable, that means the original version is more unsatisfiable. But of course, in this case, we also have the two uninformative cases. That is, if you get a restricted, unsatisfiable formula that doesn't tell you anything about the original formula. The other way is, if you get a satisfiable, relaxed formula, then maybe you relax too much, so that doesn't give you any informative instruction either. But in those two cases, we can actually deduce the satisfiability of the original formula. This is not only a theoretical thought, but it actually works in some practical cases. Those are like pretty early versions of popular solvers. This is from 2020. In this case, just by removing the third assertion, sorry, I don't have this picture on this on my laptop. It's like moved to another screen. This is removing an assertion, meaning that we are relaxing the formula. In this case, it becomes informative. That is saying that the relaxed version is unsatisfiable. So we conclude the original version is also unsatisfiable. In this case, if you want some unset cores, for example, you can also do this because an unset core of the relaxed version is also an unset core of the original version. This is another example from for CVC4, which is under approximation. You restrict the formula to some restricted form, and then that restricted form is satisfiable, and you actually get a model for the restricted form. And by using that model, you can easily find a model of the original formula. So this, but the original one is unsolvable by the solver due to some implementation or theory-specific reasons. We have different ways to do the restriction and relaxations. Many of them are very intuitive, as described before. In general, we want transformations to satisfy the following good criterions. First of all, they should intuitively simplify the formula, because the original one is supposed to be hard. For example, you want the transformation to make the formula smaller, so at least intuitively that can make it simpler to solve. And also, you don't want to modify the formula a lot, because that may render the result being useless. For example, if you restrict a formula too much, it becomes just unset. Then you don't really infer any useful information. And also, we want to be widely applicable. This is supposed to be a lightweight method, so we want to be applicable to any solver and any theory, basically. There is a unified language called SMT that is like a standardized way to express SMT constraints for many different solvers. So with this in mind, we might think of the problem in this way. You have an original formula, you can do different restrictions and relaxations, and naturally this is parallelizable. As long as you can get one informative answer on any of those candidates, you can indirectly infer the satisfiability of the original formula. I think I will talk more about the parallelization part later.
Would you take a question for clarification?
Sure.
I'm wondering if I'm right in saying that when you move from you had these three, -1, 0, 1, right?
Yeah.
When you move from 0 to 1, am I thinking correctly that you start with a 0 formula that's unsatisfiable, and you like a smaller formula that's also unsatisfiable?
Yes, the smaller could be in terms of size or number of variables.
Sure.
Yeah.
But some reasonable sense of something smaller that has the same property of being unsatisfiable.
Right.
Okay. Very good.
Yeah.
Can you remind us what is relaxation?
Relaxation is like making the formula easy to satisfy. For example, if you have if you have two constraints, you just remove one, and then it becomes one constraint. So it's easier to satisfy. So in that case, if the solver can tell you that the one constraint is unset, then you infer the original one is also unset.
For unset?
Yeah, but for set, you need to go to the other direction. If we keep the modifications to be like strictly reducing the formula size, then the modification is like forming a DAG, directed acyclic graph, because you cannot really reduce to yourself. And the search strategy is like backtracking over the DAG. It's natural, like if you relax too much to I think this might be reversed because if you relax something to set, then you shouldn't continue. Because a relaxed version being satisfiable doesn't mean anything on the original formula. The other way is like the opposite. So this is like an intuitive way to prune the search. You don't need to search until the end. And also, how about allocating the time? This is like the non-parallel case. You have a total time, you want to allocate some time to every possible candidate. This is also something that I think it could be explored further. And the parallelization part is, in this case, I think I can go back to this figure. You can launch a thread for every candidate, where each thread is calling a solver on the relaxed or restricted formula. As long as one of the threads successfully finds some informative answer, you can terminate all other threads. That's kind of in my view, it's like a special characteristic of this problem. And furthermore, it's also the case that if you are trying to restrict the formula, you restrict it. In this case, you restrict it to A1, and then further restriction might give you A2, A1 and A2, this one. So you can run two threads on those two at the same time. But once this thread gives you a satisfiable answer, you can terminate this thread, because anything starting from here will also be satisfiable. So that's yet another way to prune the search. In reality, I think it could be implemented by some synchronization primitives, or simply like if you use multi-processing, you can use termination signals. I think this is the main idea of this work, and we learned some lessons about this SMT solving area, like distributing the total time budget. Even in the parallel case, you may still distribute the time budget because you may not have enough CPU cores to do for all the candidates. And the other thing is, in reality, solvers might have tactics and configurations that you can pass through the command line or STD input, so that every solver is like configurable. If your formula is kind of special, you can use special tactics specifically designed for this kind of formulas. So you have many combinations to try until you can find the final answer. Thank you, and I'm happy to take any questions or discussions. Yes.
Can you handle cross learning in this formulation?
I think cross learning is like in the solving process, it serves as a heuristic. If you get some unsat in the middle of the solving, you just backtrack, but you keep some information that you can get from the unsat exploration. This is more like an external method, which is we don't care what is actually implemented in the solver, but we just use very simple rewriting rules outside of the solver, so it could be applicable to any internal algorithms. The combination is like very free, I think. I'm sorry?
With these changes, are you still a complete solver or incomplete solver?
You mean applying these changes to what kind of solvers?
Yeah, are you still end up to be a complete solver or incomplete solver?
In theory, it cannot be complete because of the undecidability results. So this is more like improving the solvers. So, yeah.
Quick question.
Sure.
Is this working? Quick question. So this is really nice idea. I was just wondering, you could also use this technically for slow solutions, right? Where it's not necessarily
that's
now
true.
it's just really slow, and you could just spawn the mutations and see if you get something that is useful faster,
Yeah.
right?
So I think there are two cases in reality that you can encounter in solvers. One is the solver is like running, but it's not giving the answer. The other case is it runs for some time and gives you unknown result. So I think for the unknown case, it might be more helpful because no matter how long you wait for the original solver, it's still unknown. In this case, you might spend more time, but you can eventually get a result.
Do you have any results? Sorry for the follow-up. Do you have any, like, how slow is the mutation process? Is it quick or?
The mutations should be quick because we are trying to make them very simple and very intuitive, like just removing one assertion randomly, maybe. Yeah. Sure. Yeah, I think there are many questions. Yeah.
Is there like benchmarks, or for like each solver, maybe there's a class of things they can solve? And
We only tried some, there is a benchmark called SMT benchmark, and we only tried some of them, and it turns out that different solvers are pretty different. But there are cases where, like if you try two solvers, one is Z3, one is CVC4 or CVC5, none of them can solve the formula. In that case, you can also combine both solvers with this kind of mutations. Eventually, you might get the answer.